Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers Doing the Impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind-the-scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continued to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuro Approaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTech employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTech's brain computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. And keep in mind, I do not receive any financial support from GTech and share my honest opinion supported by many years of experience working with their equipment. Dear Neurocareers podcast enthusiasts, get ready for an exciting adventure of the BCI Award Neurocareers podcast series. I'm honored to introduce our guest, Dr. Nicholas Opie. He is a biomedical engineer and an expert in endovascular brain-machine interfaces. Dr. Opie is going to share his insights on the International BCI Award winning Stentrode project, as well as his thoughts on careers in the field of neurotechnologies. Dr. Opie is the head of the Vascular Bionics Laboratory at the University of Melbourne and the founding CTO of Synchron, a neural interface company that's raised over 210 million Australian dollars in funding. His team's submission on the Stentrode, the world's first endovascular brain-computer interface device, won first place in the International BCI Award in 2021 and was listed in Time magazine's top 100 inventions of 2021. Dr. Opie and his team are pioneering the field of endovascular neural interfaces, ENIs. In this podcast episode, Dr. Opie will share his insights on what makes a project a winning one and provide suggestions for those submitting their work for an award, such as International BCI Award. He will also offer his thoughts on building a career in neurotech, including the skills and qualities that are important for success in the field, what he looks for in job applicants, and his career advice for our listeners. Are you interested in learning about the cutting-edge Stentrode project and what it takes to succeed in the innovative field of neurotech? Then buckle up and get ready for an exciting journey into the world of neural interfaces with Dr. Nicholas Opie. Let's go. Dr. Opie, thank you so much for joining us today. It's a great pleasure and honor to have you on our podcast.
Thank you for having me here.
Thank you. Can you tell us where you are joining us from and maybe some interesting facts about your lab and also the company you are leading?
Yeah, thank you for having me. It's a real pleasure to be here to talk about the work that's been going on for nearly a decade now for us and certainly longer in the field in general. I'm speaking to you from our office in Melbourne. Synchron has a couple of offices now, one in Melbourne, Australia, and another in Brooklyn, New York, in the USA. So the reason we've got a couple of offices is we started off about a decade ago working with the University of Melbourne and spun out from the university in collaborations with them and Royal Melbourne Hospital and the Florey Institute of Neuroscience and Mental Health. And we did some initial human trials with our device, which I'll obviously go into more details in Australia. And we're now expanded to the US where we can do additional trials and work to get our device approved through the FDA so that it can be a technology that the doctors or physicians can prescribe to their patients with paralysis.
Thank you so much. And now, can you tell us about your and your team's work submission for the International BCI Award and how Synchron won first place in 2021 for developing Stentrode? For those who are just getting into the field of neurotech, maybe you also could explain what Stentrode is and how it differs from all other currently utilized approaches for brain-computer interfacing.
Sure. I'm not sure how we won the award. I mean, I think we were very lucky. I think the reviewers obviously liked our project. So we're developing a brain-machine interface and an endovascular one. Brain-machine interfaces in general are technologies that capture or record signals from the brain and then convert these signals into commands or actions or switches that can be used by assistive technology. That could be a computer or a wheelchair or an exoskeleton. And the reason that these are important and becoming more important is many people with paralysis, and that can be, I use that as an umbrella term. It could be from stroke or spinal cord injury or motor neuron disease or any number of neurological conditions where your brain is fine, but the signal that goes from your brain to your body or your limbs is affected or impaired. So for these people, they're sort of locked into their own bodies. Their minds are functioning, but their limbs don't work. And so brain-machine interfaces offer them a potential solution where they can use their minds to think, and then they can control devices that they could have before the disease or damage, but can't anymore. So someone who wants to use the computer to type a message or an email, they can't do it with their hands, but they can do it with a BCI. And one of the technologies we came up with was a way to use a BCI and implant it in a really safe way. Conventionally, there are three types of BCIs. There are non-invasive ones which go over the top of the skull. There are invasive ones which remove some of the skull and then put electrodes directly into the brain tissue. And then there's ours, which aims to get the benefits of both, being safety and efficacy, by going underneath the skull but without removing the skull. And to do this, we've used the blood vessels as a pathway to reach the information-rich areas of the brain, the motor cortex. So we can reach these brains by using blood vessels to position the device called the Stentrode over the motor cortex. Once we're there, the Stentrode can record thoughts. It can record when someone's intentionally trying to move. They obviously can't move their limbs, but we can capture this information and interpret it and convert it into commands that can be used to control a computer, so they can type an email, for example.
Mm-hmm. Thank you so much. And again, for those who are not very familiar with the problem that you are addressing, what is the extent of the problem that you are trying to solve by developing this endovascular brain-computer interface?
The initial problem we're trying to solve is communication. So how can we, and this doesn't have to be spoken, it can be digital communication, so emails and texting, and really how can we return independence and freedom to people with paralysis, for people who, for one reason or other, can't use their limbs. How can we help them perform what's called activities of daily living? And that, communication is a large part of that, but there's also, shopping and banking, and there are a lot of things you can do online that will help them live their lives in a way that they can't do anymore. So how can we use technology to restore some of their lost abilities?
And how many people across the world, at least approximately, that can benefit from this type of technology?
Millions. A report came out about 5 years ago predicting that by 2025 there'd be about 50 million people in advanced economies that would benefit from neural interface technologies. Certainly that number seems to be increasing. People unfortunately still have accidents. There are still diseases that happen and conditions that people can get. So there's a large number of people that would require some help, and a BCI is one way that we think we can help them.
Thank you. And maybe you can provide some known examples of those people who lost this ability to communicate due to paralysis or some other disease. And also a question of why current approaches, such, for example, exoskeletons, may not always be the best help that is offered.
Yeah, so I think last count there was maybe 30 or 40 people around the world that have been implanted with a brain-machine interface. Some of these had spinal cord injury, some of them had amputations and loss of limb, so they were trying to reconnect to robotic limbs. The 7 people that we have implanted to date have motor neuron disease, which is a degenerative condition. There's no cure for it. There's no real understanding on why someone would get it, and you start becoming more and more paralyzed. So you might lose your speech, then you might lose the ability to use your hands, and then you can't walk anymore, and eventually you might get to the stage where you can't breathe unassisted. So the people that we've been looking at have been motor neuron disease, and for them, what they really wanted to do was communicate with their families and communities and loved ones. And so we've been able to use the technology to connect them to computers and phones so that they can send text messages or they can write emails. And for them, that was really important. As you mentioned, there's a lot of really exciting, amazing technology coming out. So exoskeletons is one. There's some fantastic robotic and prosthetic limbs. There's all sorts of electronic wheelchairs, and they're getting better as well. So there's a lot of technology that's come out, and I think given that paralysis is such a large umbrella, there are some people that would benefit from one piece of technology over the other. And I think the field needs to be aware that not everyone has the same needs or requirements, and some may like one piece of equipment or the other. But I think in general, the field is aiming to connect people to whatever they want. So certainly for us, we'd love to be able to connect people to computers, and if we can do that, then and they need a wheelchair and exoskeleton down the track, then we'd love to be able to do that in the future. And so I think there's certainly a really exciting field. There's a lot going on both in robotics as well as sort of the neural interface part of it. And I think that there's a lot of job opportunities, and certainly a long way this field can go. We're really at the start, and I think it's going to have a huge impact on the people with the conditions, their carers, and sort of society as a whole.
Thank you. And what current innovations inspire you in what you do in your research and development?
So I'm really inspired by the stories of the people and the carers that we've been implanting. Certainly one of the first patient we implanted, he had severe paralysis, and his wife, who was his carer, sort of needed to be by his side all the time, making sure that if he needed water or needed to go to the bathroom or whatever it is, that she would be able to help him with that. When we connected him to a computer and connected him to a phone, she also got some more independence. She was able to feel comfortable going into the garden. She felt comfortable going down the street and doing the shopping, knowing that if he needed something, he could just contact her with a phone in the same way that you or I use them. But they had lost that ability to communicate over distances. And so I think hearing how the technology changed her life, and she wasn't one of the people implanted, she was just a carer and a family member, how it changed her life sort of really inspired me to continue. And how can we help more people like her and like him, get back to where they were perhaps, and help them along their journey.
Yes, absolutely. So you're helping not only individuals who are paralyzed, but also their families, their caregivers. So it's a very broad spectrum of people that you are affecting with your work, with your technologies.
Yeah, no, it's certainly not something I predicted from the start. Many years ago, I thought that we'd put these devices in and we'd help the people that were being implanted. And it's amazing and fantastic to see that it is having a broader reach than that. So it encourages me to keep working hard and keep trying to deliver the next best product and make it safer and more functional than before.
Absolutely. And now I would like to talk about the uniqueness of the approach that you are using. And I think it's very well reflected in the name of your lab, which is called Vascular Bionics Laboratory. You are talking about vascular electroencephalography, and you have the whole paper on it, and the vascular techniques. So can you talk a little bit more about what that is, vascular bionics, vascular electroencephalography, so that our listeners would understand what's going on, what you are working with?
Yeah, sure. What we really want to do is get as much information from the brain as we can. And to do that, you need to get as close to the brain as possible. So while there's been some great progress done on surface arrays, so devices that go outside the skull, if you can manage to get electrodes or sensors inside the skull, then you can get even more information. The current way of getting inside the skull requires open brain surgery, where you remove some of the skull to access the brain and then put electrodes in. Now that obviously has risks involved, and historically there's been issues with infection and bleeding and so forth, which obviously will get better as time goes on. But when we started this field, we thought there must be a better way. How can we get inside the brain, inside the skull, without doing this surgery, and do it in a way that could be a day procedure, so that the patient can come in and have the implant and then leave. So we took a lot of advice or predicate from the cardiovascular field, where they are using stents to go into blood vessels in the head and remove blood clots. I looked at this technology and was thinking, well, if they can get in there with this technology, why can't we do that? So we modeled our device on a stent, and so that's where we got the word Stentrode. It's a stent electrode array. And by putting sensors on the stent itself, we can use these blood vessels to get to the brain. We don't need to pull out blood clots. The patients we're looking in, that's not why we're doing this surgery, but we can go in with a similar device and just leave it there. And it's been shown in the cardio field and now through us to be very safe over long term, and also a very safe and very fast procedure. So vascular electroencephalography, that's the field that's only really just come out through us of getting into blood vessels and using that just as a pathway to get information from the brain. And so it's a little bit different. We're not touching the brain itself. We're sort of invisible. We're hiding inside the blood vessel. And so the signals that we get are slightly different, but pretty similar to those if you were putting electrodes directly on top of the surface of the brain. And there's many things you can do with that. We've only just started, obviously, and we're just starting to look at paralysis as the first application of how we can record signals. But certainly as the field advances, then there's going to be many more applications for recording or stimulating from within a blood vessel.
Yeah, that's very exciting field. And you already started talking about that, about the similarities with conventional electrocardiography signal, for example. So what do you find similar and what do you find different between those two signals? I read some of your paper from the studies that was done in sheep. You were reporting some range of frequencies. So in ECOG, we often use high frequency oscillations for signal detection and mapping. What frequencies do you see as the main for use in Stentrode?
Yeah, I think it's different. So similar that we're getting very similar signals and very similar bandwidths, frequencies. The high gamma ones are those that historically seem to be more relevant and more applicable to intentional movements, with the aim being someone will perform an action such as move their left hand, and then the brain signal will change and we'll be able to see that the signal has changed from baseline when they're doing that action. And generally the high gamma ones are those that give that piece of information of someone trying to do a movement. That being said, there are a lot of other frequencies that can be used, and there's other decoding that can be taken advantage of to get signals out. And so I think that the field's really just starting to understand what is the best for each patient group. And certainly if you're trying to control a really sophisticated prosthetic arm, then you're going to need lots of signals, and these signals are going to have to be very different from all of the other signals you're collecting. And that's quite a different problem to if you're just wanting to control a mouse or a cursor or a button. You know, there's less switches or commands, if you will, there's less information. And is there a way that can be done in a different way to get the most benefit and make it reliable and easy to use? And so I think there's going to be different signals for the different applications or different assistive technologies, if you will, that the patient wants to use. And as I said, the field is really, it's been going for a while, but it's really just starting to understand these differences and really starting to have benefits to patients. And I think over the years to come, some amazing decoding as well as some amazing systems are going to come out to really help people maximize the signals that they can generate.
Mhm. Thank you. And in the field of ECOG recording, intracranial recordings, there is this movement towards multiple electrode arrays, increasing the number of electrodes to improve spatial resolution. What do you think in terms of that with the endovascular electrodes? Is the information that you are receiving now enough? Or you also think that there might be a need of increasing the number of electrodes of sensors within the Stentrode?
Yeah, great question. I think for the patients we have at the moment, what we've got is enough for them to be able to control a computer. What we want to do, though, is start opening the doors in the future for controlling other technologies as well. And they can be ones that exist already, like prosthetic limbs, or they can be ones that are, that only exist in research labs or are coming, are starting to be developed. So there are some sophisticated electronics and exoskeletons and so forth that we don't really know what technology is going to be available to control. So we have to be mindful that as the field increases, then getting more information out of the brain is going to be valuable. And how do we do that? And there's obviously a couple of ways. You can either put more electrodes in and get resolution, or and those electrodes can either be in the same spot or multiple spots. And so one of the other benefits of using blood vessels is there's obviously a lot of blood vessels and they go to a lot of different brain regions. And so there's, work on how do we access more of these regions to get more information, and whether we need lots and lots of electrodes in the one spot or scatter them around to get lots of different spots is something that no one has an answer to yet, but something that us and other groups are very keen on looking into.
Yes, actually, that was one of my questions, because now you're targeting one particular blood vessel, but is there an option to expand it and implant into other vasculature as well?
Yeah, absolutely. The technology might need to be changed a little bit. The Stentrode that I designed is designed specifically for this vessel. So it is delivered through a small 1 millimeter catheter and then self-expands to the 6 or 7 millimeter vessel it's implanted in. And the reason it does that is to push the electrodes against the vessel wall to allow the blood to flow unimpeded through the vessel. If we're going into smaller vessels or larger vessels, then we need to change the size of this technology, but that's a pretty simple thing to do. And certainly you're seeing that with some of the invasive technologies. They have to drill a hole to put a device in, and if they want to go to a different region, they just have to drill a different hole and put it over there as well. So I think there's going to be a limit on how many holes you can drill. There might be a limit on how many devices we can put in blood vessels as well. I guess that's something that we'll continue to look at as we go forward.
Mm-hmm. Thank you so much. And of course, a question is, how long can Stentrode stay inside the blood vessel and still provide signal that is needed to control BCIs, external devices?
Yeah. So some of the patients we've implanted have been using it for more than 2 years, and they were able to start controlling a mouse click or a switch the first day the device was turned on, and they can still do that today. So we don't know how long it's going to last for. We don't have any reason to suggest that it's not going to continue, and certainly the data we have from all of the patients is that it has continued over since they were implanted. So we're going to continue collecting that as the patients continue to use it and the clock ticks on. But so far, at least a couple of years is how long they've been able to use it for without any change in signal recording.
That's beautiful. I also saw one of your paper when you were looking at the changes in blood vessel walls with the implanted stentrodes. Can you give a brief summary of what your findings were?
Yeah, sure. Another one of the reasons we went with an endovascular approach is there was a lot of data that was coming out at the time on penetrating electrodes. So they're like small nails that you hammer into the brain and record neural information that way. There was a lot of data that was coming out to suggest that the brain doesn't like having these metal spikes in them, and it rejects them in the same way a splinter in your finger might be naturally rejected out of the body. These were occurring and sort of rejecting out of the brain. So we thought that if we put them in blood vessels, we might avoid this rejection because we're not touching the brain, so the brain doesn't know we're there. The blood vessel knows we're there, though. And so what the blood vessel does is it tries to almost push us as far away from the middle of the blood vessel as possible, which is really advantageous. And we weren't sort of expecting this, but the device, when it's opened, is pushed into the blood vessel and it's covered in a tissue, an endothelial layer. And this, we found, has actually increased the signal strength and quality over the first, say, month, after which state, sort of plateaus and it stays the same. But it takes the metal out of the blood vessel and covers it. And so there's nothing inside the vessel anymore either. And there's nothing outside the brain. So we're really part of the vessel at that stage, and the signals improved. So that was a bit of a positive that we didn't expect, but it's one that's certainly helping the system to function over the long term.
Yeah, thank you. And at the beginning, when I asked you what helped you to win a BCI award, you said that it's luck. What I wanted to say, and this I found out speaking to Dr. Christoph Guger, who was talking about the awards, BCI awards, that it takes time to develop a technology. So it took you a long time to get to the place where you are now, and persistence. In regards to that, can you give a summary of major milestones in your work that brought you to this Stentrode that you are testing right now already in humans?
Yeah, sure. So we started back in about 2011, 2012 is when the laboratory was set up. We were successful at getting large seed funding to help us develop the first technology. So the first milestone really is, I would say, animal preclinical proof of concept, where you've designed a technology, you've tested it out on the bench to see that it works, and then you've inserted it in a suitable animal model and you've shown that it's functional. The next step is to do safety testing, and so that can be preclinical as well as benchtop testing, and there's a huge number of tests that the FDA and other European or Australian regulatory bodies would like to see. All sorts of biocompatibility and corrosion resistance and all sorts of things depending on the technology. So the second milestone after showing it works is showing that it's safe. And for us, with a permanent implant, what we had to show was safe might be different from a non-invasive implant or a device that's not permanent, but certainly that's the next step. Once you have those two milestones ticked off, then that's when you start the human trial. And to do that, you also have to make sure that your manufacturer is making the devices consistently and under quality control procedures and so forth. So while for the feasibility testing, a lot of those devices are just made by hand in the lab, and we could show that, yes, it worked. Once you get to the stage of the chronic safety and the human testing, obviously, you need to be making them in a approved facility. And so me making them by hand just wasn't going to cut it. So the next milestone really is, how can you get a manufacturer, and it might be you or it might be an external partner, but how can you get your devices made in a safe and reliable way every time? And so if you get those three, you've got devices that are made properly. You've got testing to show that it works, and then testing to show that it's safe. That's when you can apply for human clinical trials, either in Australia or Europe or the US or wherever, and that's when you can really start getting some data. So before then, we had a lot of confidence that it was going to work, but until you've implanted one, you really just don't know. And so the first trials are amazing, where you really get a huge amount of information. You start getting the brain signals from humans, and you can start working on the decoders and the software to translate that information, whereas beforehand just wasn't so possible. So then the next step after you've done the humans is, okay, well, now how can you make the software? And that external side, perfect. And then obviously the next stage after that is the one we're in at the moment, doing more human trials with a device that's gone through what's called a design freeze. So you lock the device in and you just do a number of trials to show that it's safe and functional. And at the end of those trials, if successful, the regulatory body will say, yep, we'll give you approval to market the device. And at that stage, it can be sold to those who need it. So So we've got a long journey ahead of us, but certainly the main milestones are, show that it works, show that it's safe, show that it can be made properly, and then show the same in humans.
Yeah, and you mentioned so many different components and software and hardware and regulatory work that people are doing and much more. Of course, this demonstrates this multidisciplinary nature of neurotechnologies in general. So for those who might consider joining this field from various other disciplines, can you tell about your specific team? Who are those people who are making what you do possible?
Yeah. In the early stages, it was, clinicians and engineers, both electrical and mechanical, as well as preclinical experts and histology experts. And so mainly around the science, the engineering, the medicine. As we started to grow, we obviously needed a lot more business expertise. And so I think the state we're at the moment with around about 60 employees, we have skill sets that are extremely broad and go far beyond just the engineering side. So I don't think there are too many professions that wouldn't be able to find a spot in BCI. You could be from legal or finance or economics or marketing or whatever. There would be a place if this is of interest to you. So I don't think you don't need to be an engineer or a clinician. There's a lot of skills that are required as you start growing and as the device gets closer to a product. We need more and more skills, and I'm sure that there are a lot of companies around that are also going to need a huge amount of skills and very varied ones to get where they need to go.
Yes, and what maybe are particular skill sets that you are looking for in people? Maybe also some qualities, personal qualities in people that you are hiring or looking for to hire.
Yeah, this obviously changes with each company, but the things I look for, I like people that have imagination. I think that's important for what we're doing. I think it's important to have resilience, and certainly, if you're an engineer building a new technology, you're not going to get it right the first time, probably not the second, maybe not the third or fourth. But if you can keep going and keep making improvements and learn from all the mistakes that you made, then that's going to be critical. I think you also need to be open-minded and fun and have your heart in the right place. I mean, I think everyone who's working in this field is doing it knowing that the technology they're building is probably not going to help them, but it's being built to help other people. And so, that's a very important understanding where, you're not really doing it for yourself. Like, how can you help others and help society? And I think that comes out pretty clearly in some of the interviews, that there are people that are really passionate about that. And, obviously that's something that we look for.
And what is one skill without which this project wouldn't be possible? I mean, your own skill.
Probably, I think I've probably got the first two: imagination and resilience. Are the ones that have been able to keep us going. Like I was saying, I made so many of these different devices in the early days to try and get it right. How can we get a device that can crimp down, like I was saying, to less than a millimeter and expand to more than 7 millimeters? How can this device also have all these sensors on it that can pick up, vascular electrocorticography? A lot of challenges, and I and the team had a lot of fun, making different devices to overcome these. And we're happy that the one we've got at the moment is functional and is also really safe. And so that took a lot of effort and a lot of different designs, and we had a lot of fun doing it. So I think that part is probably one of my skills.
Yes, and I would agree with imagination, and many people agree because people are talking about this device as really unique and it differs from anything else that was done in the field up to date. So using the blood vessels and this type of brain-computer interface interaction. So one interesting thing that I also read in one of your papers in Nature Biomedical Engineering was that not only you are trying to record information with the sensors, but you are also trying to stimulate the brain. Can you talk a little bit more about that, and what are possible implications can this have, and how are you planning to use it in the future?
Yeah, sure. So the Nature Biotechnology paper was really a feasibility assessment. Can we stimulate different regions of the brain from within a blood vessel. And in that paper, we showed that we were able to, depending on where the electrodes were along the motor cortex, we could stimulate different ones and get different responses, which gave us some preliminary evidence that, yes, we could access and control different parts of the brain. Well, the benefits of this technology, again, is how we can make sort of existing technologies a little bit safer. So there are some amazing pieces of technology that are already out on the market for deep brain stimulation. These can be used for people with Parkinson's tremor or epilepsy, and they're starting to use it for depression. And in these, with these devices, again, you drill a small hole in the skull, and then you put a sort of a pencil-sized electrode through the brain into a very deep region. And if you stimulate that region, then people with tremors, the tremors stop. Or it's thought that if you are about to have a seizure, then you stimulate and the person might stop having a seizure. We think that there are blood vessels, as I said, that can get to these regions without having to do the surgery. And it's possible that we would be able to get a device to these regions, and instead of having to open the skull and put the electrodes through, then we can help people with other neurological conditions by stimulating to stop the seizure or stop the tremor or whatever it is. We're obviously looking at that. We're very excited about it. We're very focused as well on making sure that the BCI product gets out to market before we span too thin. I think that's a key for a lot of startups. There's, if you've made a good technology, it's very exciting to spread it out into a whole lot of different applications. I think you just have to be aware that while it's possible, it might not be the best thing to do at the start. So each company needs to think about what they're doing individually and see whether that's right or wrong for them. But certainly we've chosen to focus on the recording part of it for paralysis. But we do know that we can do the stimulating, and so there's other opportunities in the future.
Mm-hmm. Thank you. And can you give a brief summary of how your technology differs from any other currently existing neurotechnology?
The main difference is the method of accessing the brain. Other technologies require invasive surgery where they remove some of the skull and insert electrodes onto the surface of the brain or into the brain directly. The Stentrode is implanted through blood vessels, so we don't need open brain surgery, and we can still access the same brain regions as these other technologies. So it provides a safer method for obtaining neural information, and also done in a way that is more scalable around the world. There are a huge number of hospitals now that have endovascular or vascular surgeons, if you will, who use specialized theaters to remove blood clots or to fix broken blood vessels and aneurysms and so forth. We can use the same surgical procedures and the same theaters to implant our technology. So I think one of the benefits is that all the infrastructure required to insert our technology exists already, and we don't need to have specialized theaters or specialized equipment or specialized procedures. It's something that's common practice for a lot of these neuroradiologists.
Yeah, that totally makes sense. Interventional neuroradiology is much more popular among the hospitals rather than just brain surgery, like epilepsy surgery, tumor surgery, which have possibility to implant subdural electrodes or intracranial. Yeah,
Yes.
absolutely, it does make sense. What was one of the most unexpected things that you learned over the course of your research, your studies?
Yeah, I think the most exciting and magical thing was seeing that it impacted other people, not just the implantees. That came as a bit of a surprise, and it's a very pleasant one, obviously. But I didn't expect that we'd be helping anyone other than the people that we were implanting. But to see it help the families, these patients can now speak with them and speak with their society and the groups that they're involved in, and as well as their loved ones and carers. It sort of made everyone's job a little bit easier, and everyone who surround them is excited about the technology even more so than or just as much as those that are using it directly. So that's something I didn't really expect, and I think that's something that will keep the technology going as it goes further forward. Just the benefit it has to reducing the burden on carers and families.
Mhm. Thank you. And what are your next steps? What are you planning for the future in terms of developing your technology?
So the main next step is to complete the what's called a pivotal trial. We're doing that in the USA. We will implant a number of patients with the technology and show that it's safe and show that it's functional and receive approval to then market the device. What comes next on that and what we're sort of working on is some of these other neurological conditions you're talking about. How can we now expand the use of the Stentrode to other conditions? We've shown that it's safe. We've shown that at least in preclinical work, we can do stimulation. Is there a way that we can help other people by doing stimulation for epilepsy or Parkinson's or some other condition? And we're starting to look at how we can do that and how we can do it safely. And there might be another product in the future, but certainly, just making sure that we can get the first one out and do everything we need to get that approved is the focus.
Thank you so much. And what is your vision for the future of neurotechnology, and how do the Stentrode and endovascular neural interfaces in general fit into that vision?
Yeah, I mean, it'd be great to see a society where if someone does have paralysis for, like I said, whatever reason, then they don't necessarily mean that they need to miss out on being independent. It'd be great if you could control your computers with your minds, if you can control your smart homes, if you could connect to your wheelchairs and get around, or all your exoskeletons, if that was what you'd like. If your arms weren't working, then it'd be great if you could connect to a robotic limb and use them and have people playing the piano again with robotic arms. I mean, I think that there's such a huge amount that we can do in the future. There's some technology that's already out there that's amazing and fantastic. I think the brain machine interface component of it, that's also getting a lot better. And I'd love to see the Stentrode continue to be a part in this ever growing field that I think's going to be really exciting to see what happens next.
Mhm. Thank you. And how this field in general of endovascular neural interfaces contribute to the existing field of neurotechnology? What implications of this type of technology on the field in general?
There's still a lot of science and knowledge that is being gained from all of the tests that we as well as other people are doing. There are still a lot of gaps on how the brain works and why it works that way. And certainly having technology that can start to look into the brain and see how it's functioning and try and understand why it's functioning this way or not functioning in a particular way. So that might have a huge impact on how different conditions are treated. Is there a way to provide different medicines? Is there a different way to rehabilitate people? What information can we get from the brain and how it works that we couldn't get before? And I think we're starting to have a new lens on which to view the brain, and hopefully that will come up with its own field of inventions that can help a huge range of other conditions. So I think there's one side which is making devices so that people can control things again, but there's another side of like, how do we view the brain? How can we see how it works? What can we learn? How can we advance in that sort of knowledge gap that we have? And I think that's going to be fascinating as well.
Thank you. And for those who are considering their careers in the field of neurotech, can you share your path to the field of neurotechnologies and the path from where you started and where you are now? And also, who did you want to be when you were growing up? Is this somehow related to what you are doing right now?
Yeah. So look, at high school, I had no idea what I wanted to do after high school. I knew that I was really fascinated by the human body and how it worked, and I knew that I wanted to make things. And it was sort of only in the last part of my high school where I understood that engineering was a field and that you could combine science and engineering to have biomedical engineering. And so I think I was lucky that field appeared when I was finishing school. So I went to university and studied both of those things. And again, I didn't know what jobs there were. I didn't know what opportunities there were at the time. I just knew that I liked combining the two of building things for the human body. So I went to a lot of lectures that were held by various different professors. There was one, Professor Nigel Lovell from UNSW in New South Wales in Australia, who was talking about making bionic eyes and making artificial devices that could allow or help people with vision loss or blindness to see again. And I was very excited about that. And so I remember that was the first time I'd heard of people making body parts, if you will. And so I got in contact with him and said, "Can I come up to your lab and work with you for a little bit?" And fortunately, he said yes. And so from then it was just, okay, well, how can I keep going with this? So the next step in my career, and I'm not suggesting this is what your listeners should do, but just to let them know this is the track I took was to do a PhD. And the PhD for me was really a way to continue doing technology on a field that didn't exist, and there was no companies at that stage. The only way you could do this work was to do sort of academic research on it. To continue there, and then when I was finishing my PhD, there was, I had this other opportunity where, looking at neural interfaces and that was like, oh, okay, well now can I build some technology for the brain? I've done a lot on sensing and a lot on stimulation for the bionic eye. I've looked at how we can make devices that are safe and tolerated by the human body. Can I apply that in a different area? And so that's where this came to. So I think for those who are listening, I don't think there is a right or wrong path. I mean, my path is very different from all of the other people that have been hired and have joined this field. And I think really what's important is trying to go to as many lectures and conferences and things like that as you can. Some of them you'll find completely boring. That's fine. But some of them you'll get really excited about, and they're the ones that you should try and follow and try and get involved in somehow. And I think that if you find a job that you like, then you'll find a job that you'll be good at. I think they're one and the same. So trying to get yourself out there and seeing what is available will help you know which field you want to go in.
Yeah. And also one thing that you mentioned and other people in the field are mentioning as well is not to be shy to contact, to ask to work with them, like you mentioned, you also did, and you got into the lab and you had possibility to work.
Yep, absolutely. Yeah, don't be shy to reach out. Don't feel bad if you don't get responded to immediately or if you need to send a follow-up invite. Obviously, a lot of the people are very busy. It's not a rejection if you don't hear back. It might just be they didn't get the email. So I know that a few people have told me, "Oh, I reached out to this person and they didn't write back." I'm like, they might not have got it. So just it's okay to try again, and don't be disheartened if you don't hear back. Just have the confidence and know that it's okay to reach out again and ask them and tell them that you're excited and if there's a way to get involved.
Yeah, absolutely. I actually did the same when I was, we even didn't have a PhD program in my field in my country. And I reached out to a professor in Helsinki in Finland. And it was very, very successful. So
yeah, fantastic.
Yeah, I also encourage people to do this. Thank you for mentioning it. And as you already mentioned, before you got into the field of neural interfaces specifically, you worked on other body parts, you work on sensory organs, and specifically also bionic eye. Can you tell maybe about some of the main projects or a project that you are particularly proud of before you went into the Stentrode development?
Yeah, I think the bionic eye one is one that I think I'm pretty proud of. There was a huge team across Australia. Many universities and research institutes were involved in this project, and it's a difficult problem to solve. Right? How do you fix blindness? How can you help people who can't see anymore? And so the thing I really loved about that was similar to the one I'm on at the moment. There were so many people with so many different areas of expertise, and just the exposure you get to the retinal surgeons or the chip engineers or the regulatory personnel or whatever it is. I learned a lot from being with a team that had a lot of experts in a lot of different fields. And I think that was fascinating, and I really enjoy that sort of work. And so when I was doing that project, again, we did all the safety testing and then the functional testing. And then in about 2014, I think it was, implanted some humans with the technology that was designed to be safer than the other technologies that existed at the time. And there were some very good results there as well. We were able to get people to see phosphene, so they can see spots of light. And if you stimulate in the right areas, those spots of light can turn into pictures or shapes, and that can help them navigate through a doorway, or they can see if there's a post in the road that they're walking down? Can they see where a cup is on a table and things like that? So it's a long way at that stage from 20/20 vision. Like, there's a lot more resolution that's required to get to that sort of sophisticated vision. But certainly, even at that early stages, the people that were using it had incredible benefit by doing things that you or I would take for granted, right? Walking through a door and not into the wall, for example. I mean, that's something that helped them, among other things. So I think I was very proud of the work that the team did, and I'm happy that I was able to contribute in some way to that, and I think that field is still going really well. So there are a lot of different neural engineering fields. So you don't have to necessarily want to help people with paralysis or with vision loss. There's hearing, there's epilepsy. Any neurological condition now seems to have a biomedical technology that's trying to address it. So for those out there who are listening and don't really care about controlling wheelchairs or computers with the brain, that's fine. There's lots of other fields that you can get into that requires people with imagination and enthusiasm.
Yes, absolutely. I agree with that. And I remembered a lecture about people who developed first cochlear implant. Actually, their first plan was to develop an eye implant, but found it an extremely difficult task. So they changed and they modified their grant application to actually do a cochlear implant instead of vision. So what are those challenges that are coming up when you are working with vision implant and bionic eye? What's the most challenging part of that?
I think with almost all of this technology, it's how can you replicate what the human body is doing by using electromechanical devices? How do you do that? And each sort of area has its own way, right? But certainly the challenge remains of how can you replicate it, and how can you do it safely, and how can you make a device that is going to fit? And certainly, depending what you're doing, they'll all have their different constraints. So the Stentrode, for example, is constrained by the size of the blood vessel. We have to make a device that fits in a blood vessel, but also fits into the system that delivers it. The bionic eye, for example, is how can you make a device that's going to fit within an eye and have all the function? Which parts are going to be inside? Which parts are going to be outside? How can it be done wirelessly? How can it be done safely? How can you make sure it's not rejected by the body? And I think these sort of questions are the ones that are pretty similar across any implant with small sort of nuances, right? So even hip surgery, you have to make sure that you're making that in a way that's, sure, it's not connected to a camera or you don't connect it to a computer, but it has to remain in the body and be safe and be strong and perform the function of the hip that it's replacing. So I think there's a lot of technology there and a lot of similarities, but they're all very fun to work on.
Absolutely. And speaking about challenges, what was the biggest challenge in all your work across all the studies, and how did you overcome it?
I don't know what the biggest challenge is. We've had a lot of challenges. I think we've had a team that is really excited about challenges and solving difficult problems. So I think one way to overcome it is make sure that you have a team that have different opinions and different points of view. That's important. A team that's respectful and you can bounce ideas off and you can hear different ideas. And if you've got that, then whatever the problem is, then I'm sure you'll be able to sit down and come up with a good solution. You also have to be, like I was mentioning before, resilient and know that, you're going to have to probably try out a lot of these solutions and keep learning from them until you get to the one that fits. But I think if you can surround yourself by an encouraging, enthusiastic team, then that's really going to help solve whatever challenge you're up against.
Thank you. And what challenges do you see currently in the field of neurotechnologies that are preventing it from developing the way we?
I think the challenge at the moment is there's just not enough data. There's not enough implants. There's not enough information that we're getting to know, should we use this system or this system? Should we use this device or this device? And I don't think there's much you can do about that. That'll come with time. People are doing it and doing their best to get there. And I think once we start having large amounts of data and we can see the differences between, is this person the same as this person in the way they think, or what are the differences? Do I need to make things the same or do I need to change them? We don't have answers to those questions because we don't have enough information to make the right decision as in the field as a whole, right? So I think as we start getting more people implanted, we start getting more neural information, or start learning more about the brain and how it functions and how to customize different devices or different bits of software for each individual to make it the best it can be. So that's one of the issues that will be overcome, but is one that's sort of currently being faced.
Mhm. Thank you. And how willing are people to participate in this type of studies? Do you see any change that is happening from the previous years? I noticed, for example, even with students, I'm teaching a neurotechnology course, and from previous years, they are actually more willing to be implanted with the brain-computer interface. I ask question, how willing are you? And some of them are actually very willing to do that. So, do you see any change that is happening in terms of that willingness to have a neural interface?
Yeah, it's interesting. I think that some of the younger generations are more willing. They've been brought up with technology that perhaps me and some of the older generations didn't have when we were growing up. So it's not as scary to them. They're familiar with it. But I think as well there's greater exposure to what's going on in the research fields. There are companies coming out. There are devices that are going to be coming to market soon. There's more knowledge that they can see, through the media or otherwise, that this is coming out, and there's more evidence and confidence that it is safe and it is functional. So I think that there is a change, that people are becoming more excited about it, and I think that will just continue to grow, which is great.
Yes, absolutely. And you emphasized several times during our conversation the importance of imagination. And I think this is the key concept that brought this new device into the field, which is very different from anything that was done before. So, do you have any suggestions of how to develop this imagination, this innovative mindset?
I don't know. I'm not sure. I think one way to do it is to expose yourself to as much new information as you can. There's a lot of good conferences that are out there, a lot of seminars and lectures and things that are out. There's a lot of things you can read, and I think if you can try not to limit what you're learning from a particular field, and look at larger fields and see what they're doing, how can that be applied? So what we did is we looked at what's happening in the cardiac field. We're not working with the heart, but they had some things that we could learn, and you could say, that's a really useful invention that you have. I wonder if there's a way that can be applied to the brain or the system that we're developing. And I think there are a lot of technologies across a lot of different areas that have, whether it might not even be medical bionics, so are there things that are being done in aerospace engineering or what have you that could be useful? What information is out there? And if you can expose yourself to enough of that information, I'm sure your mind will start trying to put bits together and say, oh, how can we connect what I learned from the earth science to what I learned over here from psychology or whatever it is. And so I encourage people to try not to limit themselves to learning about what they already know, but try and learn about things that you don't know, and reach beyond what your area of expertise is.
Yes, actually, this is one of the things that one of our podcast guests mentioned. She's a specialist in the neuroscience of swallowing disorders. She encouraged people go to completely different conferences from absolutely different field. You might not feel comfortable at the beginning because you don't know anything about that, but it can bring exceptional things into the work that you are doing. So, which also happened, obviously.
Yeah. Oh, good. I'm not the only one that thinks like that then. Yeah, no, I agree. I agree with you. Yeah.
Yeah, absolutely. And also, how do you stay up to date with information in the field? Is there anything you do specifically, and what you can recommend to other people who are listening to our podcast?
Yeah, it's hard. I mean, it's changing. Certainly, when I started out, there weren't podcasts, so that's something you can do now that I couldn't do. And I think there's a lot of ways you can get information that some of the young kids are probably going to know better than I do on how to get it. I would be careful about misinformation. I think it's still important to try and go to sources of information that are true, or at least check them if you can. So, obviously the peer-reviewed journals and conferences and those things are ways where you can get information that is accurate. or at least has been reviewed by the scientific community as being accurate at the time of release. And so they're sort of ones I like. I like going to conferences as well because you can meet people who are talking, and you can hear a little bit more about it if it's something you're interested in. And depending on which one you go to, there might be, like you're saying, talks about things that you perhaps aren't interested in or didn't think you were interested in, at least, and you can learn more that way. So I think they're important ways to do it. But I'm always looking and searching for new ways I can find out information as it continually changes.
And maybe you can recommend some specific events, specific conferences, workshops that you think might be useful for people interested in getting into this field.
There's obviously some BCI workshops that you guys hold that are very good on, to learning what the field's doing in BCIs. There's some IEEE EMBS conferences that are sort of more general around engineering and medical bionics, shall we say, which are good. And then depending on which field you're in, you might want to go to a stroke conference, for example, and that's where I can go and hear about what catheters are being used or what technologies are being developed to access different vessels. There's medical conferences that also can be valuable depending on what sort of device you're developing. So there's some of them, but I think the individual will sort of know based on the field they're interested in which ones to go to. And I'm sure that the professors or people at the university can help them navigate through which ones, depending on where they live.
Yes, thank you so much. And our podcast is called Neurocareers, Doing the Impossible. So can you maybe say, what did you think was impossible, but you made it possible in your research, in your studies, and how did you do it?
I never think anything's impossible, just to just to put it out there. Seeing someone control a computer with their mind was certainly something that I did not expect I'd see. If you'd asked me if I was going to see that 10 years ago, I probably wouldn't have said I was going to. But I've seen 7 people do it on many different occasions now, and it's amazing every time. But certainly that's something that, I wouldn't say impossible, but would have been close to impossible if you'd asked me if I was going to see that 10, 20 years ago. So I'm happy to have played a part in that.
And how can one make the impossible possible in their career?
I think the first question is to understand what it is that you think is impossible and then prove everybody wrong. And I'm not sure how to do that. That depends on what you found, but I don't believe anything's impossible. I think you just need to come up with a creative solution and have a good team and be enthusiastic about whatever it is you're trying to solve. And I think you'll get there.
Thank you. And I'm very interested in neuroeducation. In neuroeducation, we see a lot of neuromyths and misconceptions about the brain. For example, using that we're using only 10% of the brain is one of the major misconceptions. Do you see also misconceptions from people that you see in terms of PCIs and neurotechnologies? What are those main misconceptions that you are noticing?
Yeah, I think that there's a big misconception that neurotechnology is designed to control people. It's ridiculously hard to get information out of the brain, let alone put any information in. And so the idea that everyone's trying to develop technology for nefarious purposes is just incorrect. Everyone's doing it, as far as I know, to help people with paralysis, for BCIs initially, or certainly help people that can't help themselves. And I think the society in general perhaps doesn't understand how difficult the problem that we're trying to solve is. And so they may see it as a simple problem, which means that we can do a lot more. And we can't yet. We're only recording from a very small area of the brain. We're making big assumptions on if we get this data, that means they're trying to control this. And certainly that's helping people control very rudimentary devices at the moment. But and that will improve, sure. But I think that the ability to fully understand a brain and every function that's going on in it and how every connection is done is not something that we're going to see for a little while.
Yeah, and I think here is so important to relate to people the complexity of our nervous system, and that the devices that we are using to replace certain connections are not as complex as the system itself. So, like you said, it's very rudimentary things that still need a lot of development. So thank you. Thank you for mentioning that. And what would be your main career advice for our listeners?
My main career advice would be find something you like and do whatever you can to get involved in it. I think if you are doing something that excites you and challenges you, then you'll be very good at it, and you'll want to stay there and want to do it. So that's sort of the advice I'd give.
Yes, absolutely. And this is in line with many people who already were guests on our podcast. They say you need to like what you do and really be very inspired by that. Yes, that's the key. And what suggestions do you have for those who are submitting their work for an International BCI Award? What do you think makes a project a winning one? And what's the best suggestion to prepare for the submission?
There's a lot of really amazing work that's going on, and a lot of it is very complicated work. So I always try and think about how can I write something so that someone who has no idea about what I'm talking about, has no idea about the field, can understand it. And I think if you know what you're doing well enough to be able to say it in a really easy way, then it makes the judges feel smart because they know what you're writing. And it makes it easy for them to know if they can judge it well or not, because there are so many different fields. If you are too complicated in what you're trying to say, then it might be an amazing project, but other people might just not understand it. And if you're going for this award or any others, then you need the people who are reviewing it to understand what you're doing and why it's beneficial and what problems you've solved. So it's always good to write a number of different drafts. And I think trying to get it reviewed by a friend or a family member who has no expertise in the field is going to help you say it in a simple and easy to understand way.
Yeah, thank you. And maybe also can refer people to watch your presentations about the Stentrode, where you in very simple manner explain what is brain-computer interface, what is Stentrode, with very easy to understand examples that people really appreciate and are able to understand. So I watched some of them. That's why I'm mentioning.
Thank you. Thank you.
Okay. And as we are getting close already to the end, what is the best way for our listeners to learn about your work and connect with you?
The best way to learn about what we're doing is probably to go to the website, www.synchron.com, and that has we put all our articles and journal papers up there. That's for what we're doing specifically. I think that if you look up a lot of engineering papers and try and keep up to date with, say, the Journal of Neural Engineering or Artificial Organs or some of the IEEE manuscripts, then that can tell you what's happening in the field in general. And that obviously has a list of people that are involved in that research. So you might come across something that really excites you. You'll now know who's doing that and where they are. And that's a way you can start the process of reaching out to them. And I think everyone, it works differently. Sometimes it's really good to go through LinkedIn. Emails can be fine. Sometimes if you know a professor who knows them and getting an introduction that way could be a good way to do it. For me personally, introductions are obviously really easy. If someone who's already a contact on my email sends me an email with another contact, then it doesn't go straight to junk. So it's very easy to get those and make sure I don't miss anything. But I think everyone has different ways of getting information from prospective students or people who are interested in technology. So yeah, so that's how I'd sort of try and learn about the field. That's as a general suggestion, but obviously, speak to your supervisors or teachers or lecturers and ask them about where they go as well, and then they might have different tools and techniques, and that's often a good way to do it.
Yeah. Thank you. And we will add all the relevant information where people can learn about your research in our podcast notes. So all this will be available for them. And is there anything else you want to share with our listeners before we wrap up our podcast today?
No, thank you all for listening. If you're excited about making the world a better place, I think that there's a huge scope for you in neural engineering or making biomedical or bionic devices. You don't have to be an engineer. You don't have to be a scientist. You don't have to be a doctor. There are a lot of professions that are needed in this field, and you're all welcome. And if anyone wants to, like I said, help people who can't help themselves or just have a lot of fun making some cool technology, then I think this is the field for you. So thank you for listening, and thank you for all your questions, and I hope we chat again soon.
Thank you so much. And thank you for mentioning that people from various disciplines can join this field of neuroscience and neurotechnologies. And this is exactly what we're trying to show in our podcast, that people with their own unique interests from different fields can find something to do in this exciting field of neuroscience and neurotechnology. So thank you so much for being our podcast guest, for this insightful podcast, for all this information. Our listeners appreciate that. And I wish you all possible success with all your projects and very successful development for your device. So thank you very much.
Thank you very much. Lovely to speak with you.
Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top-notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you're looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.